Welcome to the 6th video in a range of videos on neural network. In this video we're going to talk about gradient descent. Let's start with our network. We want to train this network and we basically want to make sure that the error gets less. But how do we measure the performance of the network? Well, one metric which is used a lot for this is the root mean square error. Instead of explaining it how it's calculated, I'm just going to show you how it's calculated. So what we first do is take the error per input situation. So for 0, 0, we want the output to be 0, so the error is 0.225. And we can do this for all the different situations. The next step is adding them all up, but we're going to take the square of the numbers. That has two effects. One, all the minuses you can throw away because minus 1 times minus 1 is 1 anyway. And the second effect is that if an error is bigger, the impact is also proportionally bigger. This step, taking the squares, it's from the S in the root mean square error name. The next step is taking the average or the mean, that's the M. Then we get a number. And the last step, I'm just going to shift it up to top, is taking the root. So, and then we get the final number. And this number indicates how good does the network perform. What we now can do is make graphs of changing of the impact of a different weight on the performance of the network. And what I did, I'm starting basically with a perfectly trained network already. So what you see in the x-axis is the deviation from perfectly trained weights. And the first weight where we're gonna see the impact of is the bias node connected to the bottom hidden node. And we're just gonna see what happens to the error if we change that. And again we see if it's perfectly trained, that was the 0, so then the error is the lowest. Now we're gonna see the impact of another weight, and still another weight. And we see that, yeah, we get lines with some kind of a local or global minimum, right? And the goal of the algorithm is basically to find the minimum, this point where all those weights have optimum performance. But there's a complication. Because we cannot do it like weight per weight, right? If we change something, we change everything. We change all the weights at the same time. And we don't know. I'm showing you this graph. I'm painting it, but we don't know the graph. We're basically trying to find the lowest point in this graph. But how can we find it? And I'm going to show you already a little bit of the complication, because this is what it looks like if we change two weights at the same time. And what I'm going to do is with the green dot, that's the situation of the network, and we're just going to circle through some different weights. And then you see that you basically are walking across that across that plane of the RMSE error. And what you want to do is find the lowest point, because at that lowest point the error is the lowest. But the problem is, in this case it's still simple, right? I could think of something. If I have this area, but I don't have the area, that's one point. I only have one measurement at a time. And in addition, this plane, which is now a two-dimensional plane, is in the case of this simple network actually, let's count the weights, 1, 2, 3, 4, 5, 6, 7, 8, 9, actually a 9-dimensional hyperplane. And I want to find the lowest point in that 9-dimensional hyperplane. So that's the challenge for the algorithm. And I'm going to show you what backpropagation actually does. What it does, it's designed such to do what I'm going to show you now. And what it's designed to do is called gradient descent. And what does that mean? You're going to take the path where your gradient, right? So it's like the slope of your hyperplane is such that the error is maximally lower. So you try to optimize the step you take. And you see already that in this very simple hyperplane, or it's not even a hyperplane, in this very simple plane you can see the direction which you have to take. So that's the gradient and the descent. So you're going to descend the gradient. That's the origin of the name. Well, this looks all nice, but you see already, well, this with how are you going to do this when you've got a 9-dimensional hyperplane? Well, that's what backpropagation does. At each point where it has a measurement, it changes the weight such that on that 9-dimensional hyperplane it takes the most efficient step to lessen the RMSE error. But you can see in this simple graph already there's one complication. Each time I put in a new value for all the weights, I'm making a step. What I showed in this animation is like it's really smooth. But if you want to take really small steps, it takes a long time, right? So small steps would be nice, but it takes a long time. But what you can also see, if I take bigger steps, I could jump over the local the minimum in this graph. And when you graph it out, you can even see that if I take 2 big steps, then I wind up even at the other part of the mountain, even higher than where I was before. So the tuning of how big of steps you're going to take, that's actually done with the learning rate. We talked about it in the second movie. There's still one last thing I want to address, which is now easily visible to show you. Here it's really clear what the minimum is, right? And that's because it's such a simple network, and it's also pretty linear, not totally linear because there's a sigmoid in it, but it's still easy and etc. When your network gets bigger, it can be that there's more than one minima. And basically you would like to find the global minimum, like the lowest point of them all. But could very well be that you end up somewhere else in also a minima, but not, which is not the lowest one. They call that a local minima, so global versus local. So that's another tricky thing, like, okay, I find some kind of a solution, but is it the optimal solution? And if I want to get out of that local minima, I probably have to shake it up, the network, and see if I can find wind up somewhere else. So actually there's still a lot more complications coming with this, but I hope it gives some kind of a flavor what gradient descent actually is. And what I explained in the second video, backpropagation basically does gradient descent. So all the changes, the choices in backpropagation are made such that you're doing gradient descent. Have fun!